momentum. Conservation of momentum is defined as a collision occurring between objects where the total momentum of the two objects before and after the collision is equal. So we have two types of collisions, and one is an elastic collision. So it's easiest to remember that two objects will remain separate after they collide. The kinetic energy is also conserved, and we'll study kinetic energy later. In an inelastic collision, the kinetic energy is not conserved, and the objects will stick together and proceed as one. We're going to worry about the velocity exchanges. So in an inelastic collision, you have two objects, they collide and become one object and move off together. You can also have one object that is together and something happens, it breaks apart, it's actually someone in a boat that jumps out. You have two objects after the interaction. So it can look like this as well. So our first example, we have two cars, A and B. And car A is traveling at 24 meters per second. It strikes an identical car B, which is at rest. If the cars lock together, what is their common speed? So I'm going to call A my car 1. So my mass 1 is 10,000 kilograms. It's traveling at V1I, all right, they have it as VA, I'm going to call it V1I, 24 meters per second. The other car, B, which I'll call as my 2, M2, is also 10,000 kilograms, and its velocity, V2I, is 0 because it's at rest. After the collision, they stick together. So it's an inelastic collision, and it's helpful to know the mass of the two combined. They're both 10,000, so we have 20,000 kilograms as their combined mass. So our initial equation is M1 V1I plus M2 V2I equals M1 plus M2 times the final velocity. It helps to write it down each time because you'll begin to memorize it. We are solving for VF. Now remember, cart B, number 2, was at rest. So V2I was 0. So I'm going to drop that out completely. So I'm going to rearrange with VF is equal to M1 V1I divided by the sum of the masses. So we have VF is equal to 10,000 kilograms times its initial velocity was 24 meters per second divided by the 20,000 kilograms. Notice your kilograms will cancel, and we're left with half the velocity. So your final velocity is 12 meters per second. In our next example, we have a child who's on a dock and runs into a boat. So there's the child running this way, going to run into a rowboat. So there's the rowboat. So there's our before picture. We have the child, M1, at 50 kilograms. The boat, M2, is 150 kilograms. The child's running off the dock, V1I, at 2 meters per second. The boat's just sitting there, so V2I is 0. Afterwards, there's the water, there's the boat, and there's the child in the boat. They're moving off together. They have a combined mass, M1 plus M2 is 200 kilograms. And we want to know at what speed does the rowboat move away from the dock? So it's going this way, but we don't know the velocity. Well, we don't know the speed. We know the direction. So, same equation as we used with our colliding trains. So we have m1 times v1I plus m2, that's our boat, v2I, equals the combined mass of this child with the boat and the combined velocity. Again, the boat was at rest, so that's going to drop out because v2I is 0. Rearrange and isolate your variable. So I'm dividing both sides by m1 plus m2. So we get m1 v1I, the momentum of the child, divided by the combined mass of the child and the boat. Solving for our final velocity, the child was 50 kilograms, running at 2 meters per second. Combined mass was 200 kilograms. We can see our kilograms cancel, and the velocity of the boat is 0.5 meters per second, which makes sense. Drifts away from the dock with the child in the boat. In our next example, we're going to have a student jumping to a dock from a kayak. So in the beginning, you have, it's a kayak, but it looks like a boat. That's your beginning. So relative to each other, there is no velocity. All right, so we're looking at the velocity of the student with respect to the kayak. They have a combined mass, m1 plus m2, and that's 80 kilograms because the student's 60 kilograms and the kayak's 20 kilograms. Afterwards, the kayak's by itself and the student has jumped out. So off he goes that way. So that will be V2F, and the boat will be V1F going this way. So let's write what we know. We know that M1 will be our kayak with the way I've written it. M2 will be our student in this one. We know the velocity of the student jumping from the kayak is 1.5 meters per second, and we want to know how quickly the kayak drifts away from him. So our initial equation this time is m1 plus m2 times the initial velocity equals the momentum of the kayak plus the momentum of the student. So initially, they have no velocity with respect to each other. We're going to solve for v1f, which is the velocity of the kayak after the student jumps out. And I'm going to subtract m1 v1f from both sides. So you can see that the momentum of the kayak is the opposite of the momentum of the student. Let's solve for v1f. We have negative m2 v2f, put a parentheses around that, divided by the mass of the kayak. So, using our values, we have the student leaves the kayak at 1.5 meters per second, and we divide by the mass of the kayak. So you can see that the kayak will drift away from the student at negative 4.5 meters per second, which means it's drifting in the opposite direction than the student jumped.